In a typical computer system, if the memory size is, for example, 8 kilo or 8 giga, then it is unlikely that you have only one memory chip with 8 gigabytes. You may have a multiple of smaller size. Combined together, you achieve 8 gigabytes and the like. That's the typical case in any computing system. Then if you have multiple modules with some size, for example, I want to have my computer 8 gigabytes main memory. You can buy 4 of 2 gigabytes, four of them, and then put as 8 giga. Then how do we have those multiple memory chips to configure large size memory? We have two choices of doing so. One is called a low order interleaving. Another is called the high order interleaving. So let's take a look at what that is. So before we go in detail, let me use an example. Here, this example is that we have four chips, and then each chip has 4 bytes, just for simplicity. So we have one chip, one memory chip is 8 bytes. And then we have four of those ones, so we want to make a 32 bytes memory system. So here, to have a 32 bytes memory system, 32 means 2 to the 5, which is 32. So we need 5 address lines. Using 5 address lines, we want to address 1 over 32 bytes. Let's consider as A0, A1, A2, A3, A4, like that. So if it's all 0, it's all 1, and then we can address 1 over 32 bytes. But in a physical chip, we have only 8 bytes. So physical chip is like this, which takes only 3 address lines, 0, 1, 2, since we have only 8 inside. So all 0, this is a 0, and then all 1, 1, and then all ones, it's 7. So each chip has only 8 bytes. Then how do we put together those 8 bytes chips, 4 of them together, to have as if it's a larger size memory chip, 32 bytes. So that's a memory organization to make a bigger size with a multiple of smaller size. In this configuration, we have two ways of doing so, high order and then low order. So let's take a look at what high order is. So let's consider that we have 4 chips. So we have 1, 2, 3, and then 4 chips. So each chip has only 8 bytes. So we have 8 of those, and then we have 8 of those, and then 8 of those, and the like. And each chip has 3 address lines, since we have only 8. So 2 to the 3 is 8. 8 address lines is sufficient to address 1 of 8. Like. But all together, what you want to get is, since we have 32 bytes, so we have 5 address lines. So 1, 2, 3, 4, 5 address lines. A0, 1, 2, 3, 4. So since we have 5 address lines, 2 to the 5 is 32 bytes are addressable. So what we do is high order interleaving means the least significant bits are directly connected to each of those chips in parallel. So let's connect that. So for convenience's sake, let me put a parallel vertical lines. So this one represent A0 line, and then A1 line, A2 line. So let's connect it together. So this is A0 from the first, the topmost chip, and then this is A0 from second one, and then third one, and then the last one is A0 line is connected together, and then this A0 is connected like that. So as we consider, so we are going to imagine that we have a big chip which is 32 bytes. Since it is 32 bytes, we have 5 address lines. Then internally, how do we configure 4 of those together to make it appear as 42 bytes? So address 0 is that, and the address 1 is connected in parallel, all of those 4 memory chips together. And then finally address 2 is connected something like this. Address 2, address 2, and address 2. So what you achieve here is that as we put 000 in 3 lower bits of address line, then 4 memory chips are all together working. So 000 means the 0th byte in each chip is addressed. 001 means next one in each chip. 4 of them simultaneously, since we connected this way, working. So idea is to make it happen is instead of 4 of them working together, let's just pick one by one. Then in turns, then for 8 each chip all together with the 4, we achieve 32 bits. So how do we do so is based on the observation of the addresses. So we have address 4, 3, 2, 1, 0. Then all zeros is a very beginning one, and then the very last one is all ones. Then what we observe is that next one is a 00001, and then you can go through 00 and 111. Then out of those 3 bits, what you get is 8 locations, 8 addresses. We got it. So this 8 locations is within one of those chips. And then as we continue, now 01, 000 is there. And then also you can have 111 beginning with a 10. So these are also another 8. Continue 10000, and then we have 10111. These one together is another 8 locations. Then finally 11000, and then 11111. So these are another 8. So if we connect A0 through A2 only down here, then you can see that, as you can see the bit patterns, address bit patterns, 4 of those chips are just working simultaneously. But what we can find is that the high order 2 bits, A3 and A2, are clearly distinguishing. When A3 and A4s are zeros, then we have a first group of 8, and then 0, 1, second group of 8s, 1, 0, we have a third group of 8, 1, 1, we have a fourth group of 8. So use those 2 bits. If you remember in chapter 3, we learned a module called the decoder. Decoder is we receive encoded information like 00011011, like encoded information, and then output is we just uniquely say what is that. So if 00 is there, saying that this is the one. 01, that this is the one. 10, this is the one. 11, and this is the one. So decoder, 2 by 4 decoder, 2 bits of encoded information like that. Then one of the 4 output is exclusively selected to say which is done. The example in chapter 3 was that if 00 means John, 01 means Mary, 10 means Sue, 11 means Kelly, then we give a light here. So when this light is on, means John, this light is on means Mary, and then Sue and Kelly and so on. So decoder is like that. So we can use a 2 by 4 decoder for those 2 bits A4 and A3. So when input is 00, we select this group. 01, we select that group. 10, we select the third group. 11, we select the fourth group. So that is the idea of expanding the smaller chips, size chips into a bigger one. So here what you do is we give a 2 by 4 decoder, and then two inputs are connected, A3 and A4 are connected, then it produces one of the four output. So when A3, A4s are 0, then this one will be activated as 1, and while all the others are 0. Then use this one to enable the chip. So memory chip has a enable control input. So when this one is a 1, that chip works. If 0, the chip does not work. So using that idea through 2 by 4 decoder, so we can choose which memory chip we want to enable. Yes, and this one we want to enable, and then this one we want to enable this one. So if we configure this way through 2 by 4 decoder, we choose one of the four module, one of the four chips, which is a high order bits, and then low order bits just in parallel connects to the address lines. That is called the high order interleaving. So if we do this high order interleaving, then what you find is as follows. So if I assign all zeros, so 0, 0, all zeros, then because of 0, 0, only this chip is enabled. 0, 0, only this chip is enabled. Then if we give a 0, 0, all zeros, so this is the 1, 0, 0, and then 1, and then and so on. So 0 through 7 is selected from this one. Then now it is 0, 1 is there. And when 0, 1 is provided, then through the 2 by 4 decoder, this one is enabled. And then with the 0, 1, we go through 0, 1, 2, 3, 4, 5, 6, 6, 7, 8. So this group, then so this value 0, 1 here means 8. So what you got is internally 0 through 7, but 0, 1, which is 8, decimal value 8 is present here. So effectively this memory location becomes 8 plus 0, which is 8, and 8 plus 1, 8 plus 2, and then 8 plus 7, which is 15. So 8 through 15 is a effective location of these memories. So 0 through 7, 8 through 15 is there. Now 1, 0 is applied, then this line is activated. So 1, 0 is there. So 1, 0 is this group, which 1, 0 is actually 16 in decimal value. So this is internally 0, but it's a plus 16 is there because this is applied. So this one becomes 16 plus 0, 16 plus 1, and then this one is 16 plus 7, which is 23. So address of this chip becomes 16 through 23. Lastly, if we apply 1, 1, and then 1, 1 is here, so 1, 1 is equivalent to 24 in decimal value. So this location is 24 plus 0 and 24 plus 1. The last one is 24 plus 7, which is 31. So we have achieved the 32 bits address. So 0 through 7, 8 through 15, 16 through 23, 24 through 31 is there. So with the insertion of a decoder, and then decoding is done, the high order bits up, low order bits are directly addressed to each memory chip, and then we achieve a higher capacity memory. So that is a high order interleaving of a memory chip.